Hello, welcome to Class 2, Episode 2 of Nano Seng Chem 134, Introduction to Polymeric Materials, or just Polymeric Materials. So today we're going to continue our discussion of just everyday materials and what you are likely to find in terms of their chemical structures and some characteristics of these materials that, some characteristics of the molecular structures that translate into the properties that we're familiar with as we look at these materials and touch them in our everyday lives. So last time we talked about different types of polyethylene materials. So that is this structure where this is just a CH2 unit and this is just a CH2 unit, and so it's paraffin. Sorry, forgot the N. Sometimes with low molecular weights, low degrees of polymerization, we call them paraffin materials. So paraffin wax, like candle wax, and parafilm is where N is equal to about 20 to 40. And then for larger molecular weight stuff, we have low density polyethylene, that is LDPE, which has branch points, and the branch points, again, remember, increase the free volume. They decrease the ability of the polymer chains to pack because some of them are branched. It's a little like taking some trees with the branches intact and then trying to stack them like logs. It's not really going to work. You'll get a lot more free volume in the system, and that bulk structure of stacked trees as opposed to stacked logs with all the branches removed will be a lot easier to deform, to push around. And the same thing actually happens in polymers. So then we talked about linear low density polyethylene, LLDPE. It's hard to spell without looking at the word. And the reason that linear low density polyethylene was still low density, even though it was linear and didn't have branches, is because it had a low molecular weight. Now, low molecular weight gives you an increase in free volume in the same way that that branches do, namely because it's difficult for polymer chains to pack around chain ends. So chain ends increase the free volume as well. And let me boot up my teleprompter so I know what I'm going to tell you next. So how about high density polyethylene? A good example of high density polyethylene, which is large molecular weights and generally less branching, is something like this. So this is the bottom of a gallon jug of a solvent bottle, and you can see you have a recycle symbol 2 there, and it says high density polyethylene, HDPE. Now you can have branching, but you have higher molecular weights, and what the higher molecular weights do is they have polymer chains in the system that tend to entangle with each other. So if you have two strings, for example, or two pieces of spaghetti in a big block, then they can go past each other, they can slide past each other, but they can't pass through each other physically. And that is called an entanglement, and the entanglement density, which increases the toughness and the stretchability, for example, of a material, increases with higher molecular weight. And you also have resistance to dissolution as well. So this thing, high density polyethylene, is not going to dissolve in very many solvents. So let's say high molecular weight, high density polyethylene. High density polyethylene has maybe a molecular weight of, for example, say greater than 10 to the 6th grams per mole. And this would give you an a number of repeat units, n greater than 10,000. So that's polyethylene. This is also polyethylene, right? It's called PET, soda bottles. Polyester, it's called polyethylene terephthalate. Now, it sounds like polyethylene, but it's not really chemically very much like polyethylene at all. The structure of polyethylene terephthalate is this structure, polyethylene terephthalate, or PET. Now, a couple of years ago, I was looking for examples of objects that were made from polyethylene terephthalate. So I put in PET into Google image search, and I got a bunch of images of cats and dogs. And for a few moments, I was dumbfounded. Okay, so this is polyethylene terephthalate. The only part that's really ethylene about it is this segment here, but it's really an alternating copolymer between polyethylene and polyterephthalate, which is this unit also. When people talk about polyesters, they're talking about this material. So this is just generic polyester. The reason it's called polyester is because this linkage here is called the ester bond. And polyester can be a lot of different things, but it has to have this ester linkage in it. But for example, an article of clothing that's made of some percentage of polyester will have this structure in it. Speaking of clothing, there's another material that my shirt is made of, and that, for example, paper is made of. This is just a lab tissue, and that is cellulose. Now, cellulose is derived from tree pulp. So they take the trees and they chop them up. They remove all the lignin, which is the non-cellulose structural components of the tree. And then once they filter and form these structures into fibers, you have cotton fibers. You can get it directly also from the cotton plant. That's an easy way to make cotton thread. And it is actually quite a complex biopolymer based on a carbohydrate. And it looks in general like no. Forgot one of my bonds. So you have let me start over. Forgive me. Sugar chemistry was never my forte. Almost there. Okay, this is called cellulose. So this is like paper, would, of course, draw our N here to indicate that this is a repeating structure. And these are monosaccharides. This is a monosaccharide. This is a monosaccharide. Together, it's a disaccharide. So it's a poly disaccharide, or just a polysaccharide. So you make paper and clothing. This is also cotton. Fibers are made of cellulose. Okay, so this is an important natural biopolymer. Now, how about structures like this? What is this? This is a piece of styrofoam. It's an important packaging material and an insulating material. How about this? This is a petri dish. They're totally different materials, right? No, they're actually the same. This is a polystyrene petri dish, and this is styrofoam. So it's polystyrene polymer that has been, when it was solidified, had air blown through it in a way to make it light and fluffy and a foam. Now, what's this? This is a melted piece of a petri dish. It's actually the melted top that used to go on this petri dish, and how I obtained this was taking the top and then using a heat gun to melt it like this. Now, there are a couple of different thermal transitions that happen in polymers. It turns out that this material is completely amorphous. It's like a glass. So the polymer chains, and you can have many polymer chains in a polymer sample. You could have like a mole of polymer chains in a sample, and they're like spaghetti. So in a glass, they're like frozen spaghetti. Alternatively, you could have crystallites in a polymer, or in some cases, the spaghetti chains aligned in a regular repeating manner, and that would be something we would call semi-crystalline. But forget that for now. This is totally amorphous, and it's a glass. We know it's a glass because we are below its glass transition temperature, where it goes from a solid material to something that flows. Now this had flowed and then re-solidified, and that's why it's all messed up. So what is the structure of polystyrene? So polystyrene has a structure that's like polyethylene, but every other kink in the chain, we have a benzene ring. Sometimes a benzene ring is called a phenyl group. And this is polystyrene. And we'll call it PS for short. This is petri dishes. Styrofoam. Drinking cups. Like those red beer pong cups, those are polystyrene. Now this particular polystyrene, when you have a chain in the back, this particular polystyrene doesn't have any preferred orientation of these benzene rings coming into the board or out of the board. Now, what do I mean by that? Each carbon atom is tetrahedrally bonded because it has 4 things bonded to it that are as far apart from each other as possible, which means they're at the vertices of a tetrahedron. So there's also something else bonded to this. It happens to be a hydrogen atom, remember, because a carbon atom is bonded to 4 other things, and there has to be a hydrogen atom bonded here. Now the hydrogen atom can either be pointed out of the board, in which case the benzene ring has to be pointed in, or the benzene ring can be pointed out and the hydrogen atom is pointed in. In this case, we didn't indicate whether the benzene rings are pointed out of the board or into the board. So we call this, if it doesn't matter or if it's random, we call this atactic. Atactic polystyrene. And it has a glass transition temperature, Tg, of 100 degrees C. Now, the easiest way to show how this is interesting, or what atactic means, is to show you an example of something that's not atactic, something that has a preferred direction for the bonds to point. Now this is what I mean to show here, using this solid line here, is that the bonds point preferentially out of the plane of the board. And so these wedges here mean that the benzene rings are pointed out. And this is called isotactic. Now, isotactic polystyrene is semicrystalline. Because it's ordered. Because there's a regular arrangement, and therefore this material can form an ordered structure in the solid state. Atactic polystyrene is random, and it is therefore amorphous. A semicrystalline polymer has a Tg because it's partially ordered and partially, so it has an ordered structure and it has some crystallites in it, but the rest of it is like spaghetti. So it still has a Tg of 100 degrees C, but it also now can form crystallites because there's some order here. So we have a melting temperature that is greater than 200 C. Okay, so in general, what you have is, so let's say this is an amorphous material, and you have a bunch of polymer chains that make up the sample, just like spaghetti. And this is totally amorphous. Okay, so like frozen spaghetti. When you raise this above the glass transition temperature, this material, the polymer chains can start sliding past each other, and you can deform the material just like this. So this is this. So amorphous materials are characterized by a Tg. Semicrystalline materials are characterized, so they have, later on in the course, we'll show you the exact microstructures of what these materials are like in the solid state. But suffice it to say for now that they are a mixture of crystallites, which are these ordered regions, and amorphous domains like this. So this is semi-crystalline, and it has a Tg of just the amorphous domains, but it also has a Tm of the crystalline domains. So you can think of the amorphous domains as melting at the Tg, and the crystalline domains as melting as the Tm. Now, strictly speaking, the Tg is not a melting transition because the glass transition doesn't have a latent heat of melting like a true melting point does. But suffice it to say for now that it is equivalent to a liquefaction or of the amorphous domains above Tg when you increase the temperature above Tg. So isotactic polystyrene adopts this kind of semicrystalline microstructure. Now, what do you need in order to get these crystallites? What you need is some regular features in the molecular structure. Now, of course, this isn't the only way to get an ordered structure. There's a third way, and that is called syndiotactic, where they're not all pointing the same direction, but rather they're pointing in exactly opposite directions. And this is called syndiotactic. And it also has a TG. It also follows this type of microstructure because there's some regularity here. But a polymer can never be truly ordered. You can't have a single crystal of a polymer of any appreciable molecular weight or dispersity. Well, I take that back. There's some cases where you might have a single crystal of a polymer, particularly in protein science, but whether or not a polypeptide is a true polymer is up for a little bit of debate. But suffice it to say for now that there's always some amorphous domains. So the glass transition temperature is again around 100 C, and the melting temperature again is greater than 200 C. These are called engineering plastics. This is an engineering plastic. What do I mean by engineering plastic? An engineering plastic is something that has a precisely defined molecular structure to give you a very useful thermal or mechanical property. Now, it's quite useful to have a polymer that operates above 200 C, for example, if you want to use it in electronic components that get very hot, or also automotive components, for example, if you want to make melt extruded objects that retain their resiliency under high temperature, you would use an engineering plastic. You wouldn't use some crappy commodity polymer like atactic polystyrene, because as soon as you increase the temperature above TG, the material can no longer support its own weight and effectively melts. Whereas if you have one of these two materials and you increase the temperature past the glass transition temperature, you still have the melting temperature, you're still below the melting temperature of these crystallites, and the crystallites serve to hold the material together. So that's very useful. This isn't the only engineering plastic, it's one of thousands, but it's one of the ones that's particularly famous. So of these two, it turns out that syndiotactic polystyrene is more useful because it has faster crystallization kinetics. So it's easier to inject a molten sample of syndiotactic polystyrene into a metal die in order to form a solid object than it is isotactic polystyrene, because this takes much longer to crystallize and form a solid object. And if you're talking about manufacturing engineered plastic parts, you don't want it to take forever. You want it to be fast. And this has to do with the details of the microstructure and the way that these polymer chains pack once they're in the solid state. Okay, cool. Okay, now so far we've been talking about polymers whose backbones have been primarily carbon-based. Is that the best? Is that the only thing a polymer can be? It turns out that we can have polymers that have all inorganic backbones. Now, we don't usually think of, well, you know, this sounds like an odd thing, but in fact, it's quite a normal thing. This, for example, is a piece of silicone rubber. I made this just by taking some stuff and pouring it into a petri dish, curing it, and and peeling it out. So it has a low modulus, it's stretchable, it has a low glass transition temperature, and it's all amorphous, but the reason it's held together and doesn't drip is because it's cross-linked. And that's something we'll learn about later. It turns out that the polymer chains themselves have chemical bonds from one to another. And that's from one polymer chain to another, and that serves to keep the structure together, even though room temperature is enough to be above the glass transition temperature, which in this case is actually below 0 degrees Celsius. Remember I showed you this hard epoxy piece that was like a single molecule. Now, now this is also cross-linked. Remember, it's cross-linked with that triethylene tetramine. So this is like a single molecule, although it has some individual molecules that are probably unreacted within this. You can definitely draw a line of a percolated network of bonds from one end to the other in macroscopic dimensions. So it's effectively a single molecule. Same thing with this guy. You could draw a line of bonds from one end to another that would give you, that would show you that this thing is chemically contiguous from one hand to the other. So this is silicone rubber. Silicone rubber does not have a carbon-based backbone. Instead, it has an alternating silicon, oxygen, silicon, oxygen. Now, silicon is like carbon, so it has to have 4 bonds too. So what it has is this group. It has these little rabbit ears. And these are just, this is just a CH3 group and a CH3 group. These are called methyl groups. Methyl just means CH3, like methane, which is CH4. Ol if it's attached to something else. Ane if it's just attached, if it's just a hydrogen atom. So methane would be CH4. And these are methyl groups. So this is polydimethylsiloxane, or PDMS, which is one of the most famous polymers in all of materials science, and it's used ubiquitously anytime for sealing applications, for medical implants, for lubricating joints of machines. Now, in that case, it's not going to be cross-linked because it's a gooey, a viscous liquid. But if it's cross-linked, it's called silicone rubber, or just silicone. And it's we say that this is an elastomer because its Tg is less than room temperature of 25 degrees Celsius. Any polymer can become an elastomer if you are operating above the glass transition temperature of the material. Okay, another material that is that's pretty well known is polymethyl methacrylate, and I don't have a sample of it with me, but if you have a poster frame that has a front transparent plastic cover that's hard and it's like, you know, a big sheet, then that's probably plexiglass, which is an acrylic polymer called polymethyl methacrylate, and that has the structure like this. This is called polymethyl methacrylate. Or PMM. MMA, and it is used as a photoresist. Photoresist is used in semiconductor manufacturing to make chips. So what you do is you coat a surface with PMMA or another type of photoresist, and then you shine light through a mask. Then you develop the regions that you've shined light through. So this becomes soluble where you shine the light, and then you can etch the silicon and make your transistors and your other components on the chip using a material like this. This is a photoresist. It's also called acrylic. So acrylic, paint, acrylic nail polish, acrylic polymers, or you could call it, I think the trade name is plexiglass, which is used sometimes for optical applications where you need to make a big sheet of something. This is a very tough material, so it's not going to shatter into a million pieces like for example some other types of glassy materials might. Now there are a couple of different kinds of rubbers, natural rubber and synthetic rubber, that have a structure that has a lot of unsaturation in it. So, for example, this is called cis polyisoprene. Or latex. Latex rubber, just like latex glove. And you can cross-link this using sulfur, which is a process called vulcanization, which is how tires are made. And it makes them, so you vulcanize this in the presence of carbon black, and then you get hard, tough rubber where that you need in applications where the rubber meets the road. And since this is on video, I can't see you all roll your eyes at how stupid that joke was. Okay, so we have other kinds of rubber too, like nitrile rubber, which has this structure. This is called nitrile. Polyacrylonitrile copolybutadiene, which is this segment, and that gives you this material. It tends to be more chemically resistant, which is why it's used in chemical laboratories. Just a couple of other interesting materials that have high tensile strengths due to structural rigidity instead of materials that have a lot of free volume in them, like the rubber materials that I just drew. Structures like this is called kapton or polyimide, and it's used quite often in high temperature electronics applications. And it has the structure So this is polyimide or Kapton is the trade name, and this is for high temperature applications. Another structure you might find is something else that has, so this has high tensile strength, for one, because of its structural rigidity, so it's hard to deform fibers of this material. It tends to be highly aligned, the polymer chains, just based on the rigidity of the chemical structure. And another material that has a lot of tensile strength is a polyamide like nylon. This is called nylon 6,6, and what it is fishing lines and zip ties. What's a zip tie? A zip tie are these things. So this is what you use to clean up the wires behind your TV and sound system or computer or something. They also make cheap handcuffs. Hopefully you don't have much experience wearing these, or depending on what kind of person you are, maybe you do want to wear them. But anyway, okay. One more kind of conventional type of polymer. How about this? This is electrical tape, also known as polyvinyl chloride. So anytime you see vinyl, something, vinyl like a record, that is an LP, a polyvinyl, a vinyl pipe, for example, we're almost always talking about this material called PVC, which is polyvinyl chloride. PVC. Anytime you see vinyl, what this is derived from is polymerization of something that looks like this. This is vinyl chloride. And then the last polymer sample that I wanted to show you was something that's that comes out of the research lab, something that, for example, my lab works on, which is called a semiconducting polymer. And a semiconducting polymer, it has an arrangement of alternating double and single bonds along its backbone. So this is called poly-3-hexyl thiophene, or P3HT, which is like R2D2's brother or something like that. And what you get, and this is a semiconducting polymer. Semiconducting fluorescent polymer. And And what you have here is an alternating arrangement of single, double, single, double, single. Then if we drew this structure out, because remember this is just a repeating structure, we would have double, single, double, single, double, single bonds. And if you have alternating double and single bonds, you tend to get a band gap in the visible region, and you have a material that can transport charge if charges are injected into it. So this is an example of poly-3 hexylthiophene. I might have even made this. A few years ago. I don't know if this is one of my samples, but anyway, this is what it looks like. It's dark red. But what's cool about it is if you take a UV light and you irradiate it, it becomes fluorescent. So this is a long wave UV light, and you can see that it's kind of glowing fluorescent. Pretty cool, right? So you can actually make these that are all the different colors of the rainbow, and you can use organic light emitters like this to make, for example, OLED TVs, which are now sold commercially. You can buy them at Best Buy or Amazon or whatever. Although in those particular cases, they use white organic light emitting diodes, and they illuminate each pixel individually, and they still use color filters that are used in LCD displays. Okay, another topic that I wanted to mention before we end today's lecture is the concept of molecular weight. So the molecular weight of a normal molecule in chemistry from a chemistry class is pretty easy to define, right? You have a molecule where the molecule is all the same. Every single molecule is the same. So you have one molecular weight, one molecular weight. In the case of a polymer sample, for example, this polystyrene dish could be, I don't know what the exact number is, but you have probably 10 to the 10, 10 to the 10, 10 to the 15 molecules in this one object. Now remember I said that a cross-linked polymer could effectively be thought of as a single molecule. Most polymers are not cross-linked. Most polymers are really just collections of molecules that happen to be long enough and have enough van der Waals bonds between them to form a solid object, even though this is many, 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 many molecules. So each molecule in this object has a little bit different molecular weight. You can't make them all exactly n equals 10,000. You might be able to make some distribution of 8,000, 8,500, 9,000, 9,500, 10,000, 11,000, and so on, that followed some kind of distribution of molecular weights. And there are a couple of different ways to characterize the molecular weight that you're interested in. Okay, there are two types that we are going to talk about. You can imagine the number average molecular weight. This is the conventional average, and it has the symbol M sub n. This is the number average, or conventional average. And by conventional average, I mean exactly what you think of as an average. So you take the number of objects, you add up the weight of the entire sample, and you divide by the number of objects. And whatever the weight is the average weight. It's just like the weight of some stones in a box that are all of different sizes. That would be the average. And how you get that is, of course, we know how to get an average, but mathematically what that looks like is the summation over degree of polymerization I of n sub I times m sub I over the summation over I of n sub I, where n sub I is the number of molecules with degree of polymerization I, so for example, I equals 1, you have a monomer. I equals 2, you have a dimer. I equals 3, you have a trimer. And you can imagine having I equals a lot of different things, right? So it could be I equals 10,000, and then it would be a 10,000 mer. So you take, so the number, n sub I is the number of molecules in your sample or in your object that have a degree of polymerization I. And m sub I is the molecular weight of a molecule, of one molecule in the system, of one molecule with degree of polymerization I. Okay, then we have, isn't that good enough? You know, couldn't we just calculate the molecular weights using the conventional average? No. And here's why. Well, we can, but it doesn't give us the most information. So here's why. Instead, so imagine two types of two polymer samples. You have one with consisting of a single polymer chain with a molecular weight of 1,000,000. Picture another sample. It has two polymer chains in it. One of them has a molecular weight of 1,000,000, just like the first. And then it has another polymer molecule in the sample that only has a molecular weight of 10. Maybe that polymerization didn't go so well. Well, 10's not really realistic. Say it's 100. That polymerization reaction maybe was unfinished or got quenched by some impurity in the reactor. So you have one with a molecular weight of 1,000,000, another with a molecular weight of 1,000,000, plus another molecule with a molecular weight of 100. These two samples will behave almost exactly the same in terms of their mechanical properties and thermal properties, and probably optical properties as well. But the conventional average says that this one has the molecular weight of 1,000,000, 1,000,000 divided by 1, and this sample has a molecular weight of about 500,000. So 1,000,000 divided by 2, because there are technically two molecules in the system. Now, the molecular weight has an immense influence on the mechanical and thermal properties of a polymeric system. So if you have these two samples, you would expect that this one would be a lot different because it has a molecular weight that's half, even though it's dominated completely by the presence of one large molecule. So we need another way to calculate this that takes into account the largest fractions of the material within the sample, and that is the M sub W, which is the weight average, the weight average molecular weight, which is defined as the sum over I of W sub I, M sub I, over the sum over all i's of W sub I. And we have a new variable here, and that is W sub I, which is the the weight of the entire sample with the degree of polymerization I. Now, W is also, since it's the weight of the entire sample, you could also express it as the product of N sub I times M sub I. So you could also, if you wanted to, write this as the sum of N sub I, M sub I squared over the sum of N sub I times M sub I. Okay, let me do a quick example of how we calculate different values, and then we'll be done for today. So imagine we have two samples of 10 polymer chains each. Okay, sample 1 has the molecular weights of 10,000, 11,000, 12,000, 13,000, 14,000, 15,000, 16,000, 17,000, 18,000, 19,000. Our MN, and for homework, see if you can get these numbers to work out, is 145,000 in the numerator divided by 10 equals 14,500. Grams per mole, or sometimes in polymer science, grams per mole is called the Dalton, DA, the least popular of the James Bond actors. And M sub W is 2.18 times 10 to the 9 over 145,000, or 15,070. Now I'm going to define something called the polydispersity index. Or PDI, public displays of indifference. But the International Union of Pure and Applied Chemistry doesn't like using polydispersity index, because what does it mean to have a polydispersity of 1? You're monodisperse, but then it's not disperse at all. So what it's called instead these days is just the dispersity, which is just this D with a line through it. And the D with a line through it, or the PDI, you'll still see this, so I'm still gonna use it. The PDI is MW over MN, and in this case we have MW over MN of 1.04, which is actually quite a narrowly distributed sample. Even though it looks like it's pretty widely distributed, in the world of polymers this is not considered as being very disperse at all. Usually polydispersity indices are over 2. for example. It can be over 2. But being close to 1 is good. So, okay, this works because MW, by the way we defined it, is always greater than MN. All right, now imagine sample 2. Where suppose when we were doing this polymerization reaction, the reaction didn't happen 5 times out of the 10 chains. Say 5 of them were duds. So we have 10, 10, 10, 10, 10, but then it starts working again. Then we have 15,000, 16,000, 17,000, 18,000, 19,000. In this case, what we have is MN equals 85,050 over 10, or 8,500. And M sub W is 1.45 times 10 to the 9 over 85,050 equals 17,100. Now, how about, so in this case, the PDI is a little bit more realistic. So the PDI, or just the dispersity, is 2.01. Okay, one more little factoid, then we're done, I promise. So the degree of polymerization I is always written with an I when we're talking about molecular definitions of molecular weights, but but when it comes time to do the math, it's actually a lot less confusing to see it as X's. You use X instead of I. So forgive me. We're pretty much, unless we're talking about molecular weight calculations where you always do a summation with an I, we're going to switch to talking about degrees of polymerization primarily in terms of X, so X units. Degree of polymerization I, we're going to say this is X for most of the time in the course. X equals 1. We have a monomer. X equals 2 is a dimer. X greater than 5, but less than about 20 is an oligomer. Remember, I said this is a little like learning a language. It will get easier, I promise. So greater than approximately 5 is an oligomer, and if we have greater than approximately 20, we are in polymer, the polymer regime. So thank you very much for your attention, and I will see you next time.